All right, today we're going to dive into a really clever, almost magical shortcut in machine learning called the kernel trick. Think of it as the secret sauce that lets simple, straightforward algorithms tackle incredibly complex problems. And here's the best part, they do it without even breaking a sweat, computationally speaking.
Okay, so to really get this, let's kick things off with a super common problem in machine learning. How do you separate different groups of data?
So take a look at the left side here. That's the easy stuff, right? A single straight line cuts right between the blue dots and the red dots. No problem. That's what we call linearly separable. But then, look at the right. This is a whole different beast. You've got one group of dots literally making a ring around the other. You can try all day, but there's just no way a single straight line is going to separate those two. And that, my friends, is a non-linear problem.
And that really gets to the heart of it, doesn't it? I mean, linear models are great. They're fast, they're easy to wrap your head around, but they just hit a brick wall when you throw nonlinear data at them. So, what do? What happens when a simple line just isn't going to cut it?
Well, what if the problem isn't actually the line itself? What if it's the space the data is living in? What if we could just change our perspective?
Okay, let's go back to that tricky ring problem. Just picture those dots drawn on a completely flat 2D sheet of paper. Like we just saw, there's no way to draw a straight line to separate them, not on this flat surface.
But what if we could bend that piece of paper? Imagine we add a third dimension, a z-axis, coming right up out of the screen. And now we start to lift that outer ring of dots upwards, kind of bending the paper into a bowl shape.
Now from this new 3D perspective, something amazing happens. The problem? It's easy again. It's linear. A simple, flat plane, like a sheet of glass, can just slide right in between the dots at the bottom and the dots we lifted up. Just like that, we took a nonlinear mess and made it simple by popping it into a higher dimension. Okay, this seems like the perfect solution, right? I mean, anytime you have a tricky problem, just bump it up to a higher dimension. But as you've probably guessed, there's a catch, and it's a big one. I mean, this is a seriously powerful idea, so why don't we just do this all the time? For every single machine learning problem. Well, this quote just nails it. The problem is the sheer cost of doing it. This new, higher dimensional space, it can be absolutely massive. We're talking thousands, millions, sometimes even infinite dimensions. Trying to actually calculate the new coordinates for every single data point, it would be ridiculously slow, and it would eat up way more computer memory than you could possibly have. So the real puzzle is this. How can we get all the benefits of that higher dimension? You know, that nice, clean separation, without actually having to go there and pay that insane computational price. Okay, this is where things get really, really clever. It turns out that a lot of these linear algorithms have this fascinating quirk. To figure out where to draw that separating line, they don't actually need the full exact coordinates of every single point. Nope. All they need to know is the relationship or the similarity between pairs of points, and that whole relationship can be boiled down to just one single number, which we get using something called the dot product. You can think of the dot product as just a way to measure similarity. It basically tells you how much two vectors are pointing in the same direction. So, if that one number is all our algorithm really cares about, maybe, just maybe, we don't need to compute those gigantic high-dimensional vectors at all.
And that is the magic. That is the kernel trick right there. A kernel is just a special function, a shortcut, that lets you plug in two of your original simple vectors, and it spits out the exact same dot product you would have gotten if you did it the hard way. You know, by transforming them into that crazy high-dimensional space first, and then calculating the dot product. It's an absolutely brilliant computational cheat code.
All right, I know that's a bit abstract, so let's make this real. Let's walk through a simple example to see how this actually works.
So we're going to use a really common one. It's called the polynomial kernel. And the formula looks super simple, right? All it says is take the dot product of your two original vectors, x and y, and then just square that number.
Okay, let's actually run the numbers. In step 2, we do it the easy way, the kernel way. We take our two simple 2D vectors, get their dot product, which is 11, we square it, and boom, 121. Super fast. Now, look at the rest of the steps. This is the hard way. This is what we're avoiding. We'd have to use that messy transformation function to turn our 2D vectors into new 3D vectors. Then we calculate the dot product of those much more complicated vectors, and what do you get? You get the exact same answer, 121.
And that right there perfectly shows the power of this idea.
We got the answer that exists in that complex, higher dimensional space, but we never left our simple, original space to get it. We got all the power, all the benefits of that higher dimension with none of the computational pain. That's the trick.
Okay, so let's zoom out for a second. What's the big takeaway here? What does this all mean for us?
Really, the kernel trick gives us the absolute best of both worlds. For one, we get to use our simple, fast, reliable linear algorithms to solve messy, complex, nonlinear problems. Two, we get to do it without that insane computational cost because we never actually transform the data. And maybe coolest of all, since these kernels are just clever ways of measuring similarity, you can design them for almost any kind of data you can think of. Not just numbers in a list, but things like sentences, protein structures, or even connections in a graph.
It's just such an elegant idea, isn't it? A beautiful mathematical workaround that shows how just changing your perspective can turn a seemingly impossible problem into a simple one. And it really makes you wonder what other incredible shortcuts are out there in all corners of science and technology, just waiting to let us solve impossibly complex problems with surprisingly simple tools.